Hi, welcome to the Signal Path. In this episode, I have another product review for you guys from Signal-Hound. Last time we looked at the real-time spectrum analyzer that they have, the SM200C, which works up to 20 gigahertz, and it has a 10 gigabit Ethernet, allowing it to digitize 160 megahertz of bandwidth and stream it continuously. With a terahertz per second of sweep rate and a phenomenal speed, it was kind of a dream software-defined radio, essentially. But now, finally, they've released the SM435C, which is a 43.5 gigahertz instrument with essentially the same sweep rate, but of course many more pre-selector filters and conversion stages, but it doesn't sacrifice the speed of the instrument. It still has the Ethernet interface with 160 megahertz of continuous streaming through the entire band. But it also has another trick which I'm really excited about. Now, because at millimeter wave frequencies above 20 gigahertz, you generally have higher bandwidths that you need to work with, and that's the whole point of being at those frequencies. It does have an option with a wideband IF output that you can have added to the unit. And this gives you an 800 megahertz output anywhere in that 20 to 43.5, roughly in those frequency ranges, so you can connect that to another instrument and digitize a wider bandwidth if you want to. Of course, you can still get the 160 megahertz anywhere in the band that you want to. And it gives it a lot more flexibility because you can use it as a low noise, low phase noise down conversion stage with pre-selection and everything anywhere in the band above 20 gigahertz. So that's pretty exciting. I want to try that out as well. I also want to know how they fit all that in essentially the same form factor, because this is a lot more complex than the original SM200C. So we should do a full teardown and really understand and analyze it. And the software continues to evolve. So I want to see some of its new features as well. So let's get started. And here we have the Signal-Hound SM435C sitting on top of the Signal-Hound SM200C. Now, I have done an extensive review on teardown of the 200C model. I'm not going to repeat every single thing here, so I really recommend that you watch the review of the 200C to get some of the other subtleties and details of how the GUI and the instrument actually works while we focus on the 435 in this video. Now, if you look at the interfaces, they're essentially identical, except that we need to now have a different connector instead of the type N connector we had on the 200C, because we're covering all the way up to 43.5 gigahertz with the 435 model. And we have the same 10 gigabit Ethernet optical interface because these are both the C revisions of these instruments. Power supply is the same. We have the same IOs for 10 megahertz and so on. Now, there is one other difference here, which I'm excited about in testing, is that the 435C now gives you a wideband IF output for frequencies above 20 gigahertz or 24 gigahertz or so, and that allows you to digitize directly from here an 800 megahertz wide channel for the millimeter wave frequency range. Now, this is really handy because a lot of standards above 24 gigahertz, especially in the millimeter wave for 5G and so on, use a wider bandwidth, and you want to be able to digitize that using a very low phase noise linear and filtered front end like the one that is inside the SM435C. So it's a unique feature of this instrument, and you don't have to get this option. Of course, if you remove it, you just get the 10 megahertz output like you have on the 200C. There is a small caveat with getting this. It does reduce the sweeping frequency a little bit, but I'll talk about that in detail during the teardown of this instrument, so you can see exactly the architecture of how it is put together. And they constantly add features, of course, to the software. I'll put on the screen now a couple of the important datasheet parameters of the 435C, but really for the complete details, you really need to go and take a look at and see what's going on inside the datasheet. Now, there's a bunch of experiments I want to do, but it's important to understand how complex something like this is in this form factor and how the front end looks like and how they put it all together. So let's take a look at the boards inside and then do an extensive analysis of it. So these instruments are very well shielded because they're so compact. So I'm not going to take apart mine because it would be difficult to really get it back to this factory default condition. But I do have the boards, so we can take a look at them, and look how beautiful these boards are. So we have two boards. One is the RF board, and they're sandwiched in the middle with a few RF connectors and DC and digital connectors to the other side where all the digital activity happens. And this is quite common as to create a multi-board situation in order to be able to get the signals across and basically put all the digitization on one side and put all the RF functions and mixers on the other side. But there is so much happening on this board, and we really should understand the architecture of it a little bit and look at individual components and the signal path, no pun intended, of how it works. So let's try that. So let's take a look at the architecture of the SM435C. Now, what you're looking at is the original architecture of the SM200C that we looked at in the previous video, and this was already fairly complex because you have these large banks of pre-select filters followed by gain controls and attenuation, and then further banks of filters. This is required in order to get all the images out of the way and to make sure that you have a very good spurious free dynamic range in the entire sweep of the spectrum analyzer from DC to 20 gigahertz in that situation. There are actually more than the number of mixers that you see here, but these are all IQ down converters. And there's also a whole bunch of filters on the LO path that are not shown here. So in order to take that architecture and then extend it so that it works up to 43.5 gigahertz is a monumental task, from frequency planning, RF planning, and of course fitting it into roughly the same form factor as we saw. And this is what that architecture looks like. So we're essentially doing the same thing. We have a front-end attenuator which then switches into a whole bunch of filter banks, and all these filter banks have to also be switched together in order to be able to meet the entire range in a seamless way, because the user doesn't care what kind of preselectors there are. The user just wants to see a very good spurious dynamic range, and the user wants to see that terahertz per second sweep rate all the way to 43.5 gigahertz, which is really, really impressive. Similarly, we have gain control stages afterwards again, and then yet another banks of filters. And there are actually 5 mixers that are required in the 435 model, as well as a complete direct conversion version for frequencies below 160 megahertz, and that then makes the entire frequency range. And as I just said earlier, there are also LO filters that need to be placed in there. Now, you have to keep in mind that this is a unique architecture in a sense because there is no YIG selector here. With a YIG, you're going to have a very different architecture, but then you wouldn't be able to do the streaming of 160 megahertz, and the YIG needs to be taken out, and it basically ends up being in a similar architecture at the end of the day if you want to have the real-time capability. So this is not to be mistaken with a traditional spectrum analyzer, for example, that just looks at a very narrow frequency range. This is a totally different story and very difficult to do, of course. So here's the PCB. Now I went ahead and I put some labels on some of the components that are critical, and I wanted to talk a little bit about how they've put it together and what are the ways that you can actually quickly understand the architecture of something as complex as this without really digging into the details. So I put just some of the crucial ones. So all the green labels are the RF paths, and all the red labels are what I think are on the yellow path. And there's a couple of yellow ones which are the IF, and the mixers are in orange. So as we said, there should be about 5 mixers at least, and we can see that there is a mixer covering 24 to 44 gigahertz. That's the upper end of the mixer, and this mixer is quite unique because it does have IQ down conversion as well as IF. I'll talk about that in a second. There's another mixer over here, mixer over here, mixer here, and here. Now all these mixers are going to need an LO, and these are direct conversion mixers, so you're going to need LO to essentially reach into those frequencies as well, which has its own complication. Now all the LO essentially is generated here using, at the heart of this, one synthesizer. That synthesizer is right over here. It's an analog devices part, and it essentially works from almost from DC to 16 gigahertz. Now, of course, at 16 gigahertz, you're not going to be able to down convert frequencies up to 44 gigahertz. You're not going to even be able to do down convert frequencies of 20 gigahertz. So there is actually a doubler here, and the doubler is used to essentially get to 32 gigahertz. Now that's still not enough to do 44 gigahertz down conversion. And if you look at the block diagram of this, I'll put it on the screen. This actually has a built-in ×4 frequency multiplier. So the combination of the internal multiplier of this one, the external multiplier over here, and the synthesizer will basically cover all the frequency ranges. And the reference to the synthesizer comes from the other board, which is a DDS, which is a 1 gigahertz DDS, as we will see. Now there's a whole bunch of switches and amplifiers in the way of the synthesizer, as to be expected, because you need to boost it, you need to select between different filter banks so that you have a nice, clean LO signal, especially when you multiply it and you want to make sure it has no spurious tones that can hit these mixers. These mixers are really broadband. And if you hit these mixers with different harmonics, you're going to down convert noise or signals out of band into the signal, and you cannot differentiate then which one is the real IF you're looking for. So it becomes a very big problem. In those situations, you can always do software pre-selection, but software pre-selection is slow and it's not really foolproof because it depends on how fast the signals are changing. So if you're familiar with software pre-selection, you'd know that it would slow this instrument down quite a bit. So I don't believe they're not really doing that in any significant way, at least. And then we have mixers that cover up to 20 and up to 27. And all these mixers are always coupled with a gallium arsenide amplifier, either on the LO path or of course on the RF path. And that also helps us see the frequency planning. So for example, an amp over here in the RF path covering 2 to 20 gigahertz tells us that that signal has to reach a mixer roughly in the same frequency range, because these are direct conversion systems. And the switches that you see here are parts of the filter bank sitting in the RF port. Similarly, if you have a mixer up here that works from 24 to 44 gigahertz, we're going to have an amp that gets you essentially close to those frequencies, and it's exactly what is happening over here. Now this mixer, as I said, is unique because it does have an IF output as well in the upper end of its frequency range, and that's why you can get away with a frequency that's slightly lower. Then there's an amp here, 17 to 27. Of course, a mixer covers the same frequency range, and an LO amp right before that mixer, again in the same frequency range. So it all lines up quite nicely. Similarly here, an LO amp 5 to 18 runs up roughly to the mixer that probably only goes up to 18 gigahertz or so, because you do have 17 to 27 covered here. And there are switches here, and there are filters, you know, embedded in here that we cannot see. I'll show you the X-ray in a second so you can see how much there is in there. And then there is some more filters over here and switches to select with different bands. All those are the filters for the RF path. Now these filters up here, these are clearly for the lower frequency sides because they're so much larger, and they need to be because the frequencies, of course, is quite a bit lower, and therefore they are close to the mixers that cover the lower frequency ranges, less than 6 gigahertz in that case. There are digital programmable attenuators scattered all over the place. There are transformers and many switches in order to switch all the different IF signals generated by all these different mixers to ultimately reach the ADC, which is sitting on the other board. And there is a switch over here and a switch over here with many paths going in there, programmable attenuator, and on the other side of this board right over here are the connectors that bring those IF signals into the other board. And that's how these things essentially interact. There's also another connector somewhere around here which brings the reference to the synthesizer also from the other board, and the rest are control and power. But take a moment and appreciate how beautiful this design is and how complex it must be to make sure that these signals don't talk to each other, that they're protected from each other, there's no interference. The frequency planning must be an absolute nightmare. Look at how many soft filters they have to put next to each other just in this bank for the upper frequency range. I really like this. For the price point that you would pay for some instrument like this and all the software development, I really think this is an excellent bang for the buck for sure. And we'll see its performance and play around with it, of course, during the experiment. So here's a couple of x-rays. So I took a few x-rays of different places and I superimposed them and aligned them to where exactly those traces are in the visible on the top layer. So if we go back and forth, you can kind of see that they do indeed line up with what's underneath. And if you look all these hidden filters inside of the PCB. There are even the ones that are in the intermediate layers. There's a little bit harder to see. There's some more hidden ones over here, hidden filters over here, some other match length lines over here, and all of these filters have to be individually characterized. And my X-ray only goes up to 35 kilovolts, so it's hard to see through these PCB layers because there's so many layers and there's so much metal to make sure that these things are isolated. But going back and forth shows you the magic of the RF that's hidden even from the site by the amount of work that needs to go. It's just nuts. I think it's a wonderful design. Now we can take that and think about what do we do with the IF signals. But once you have the IF, especially once you have the I and Q, relatively things become simple, because with very good ADCs that are available, you can actually digitize that right away, go over a JSD interface, and then do some correction. And these corrections are now done entirely in the FPGA. These are essentially calibration coefficients and so on. And you can see it even says here, this is unique to the LO. So they have to pre-program all of those and characterize this and figure out what those coefficients have to be. And then you do digital down conversion, you do some decimation, and then everything else is done purely in the digital domain. Bunch of signal processing. They of course have to write all this code too, because it works uniquely with their hardware. And all of these loops and all of these things that run sequentially have to hit that terahertz per second sweep. So think about what happens when this thing runs from DC to 40 gigahertz. All these switches are switching rapidly, the synthesizer is sweeping back and forth, and they meet all those timings to hit that incredible sweep rate. So it's really impressive. So this is what the board looks like, the digital board. Now of course we have a crystal oscillator here. This is an oven controlled crystal oscillator at 100 megahertz. This gives us our frequency stability. This thing does have an excellent frequency stability as a result of this. And there is our DDS. This is a 1 gigahertz 14-bit DDS that is used as a reference for our synthesizer on the other board. And here's our main ADC, which is can go up to 1.24 gigasample per second 14-bit, I believe. I hope that's correct. And you can see the IF lines going in. It actually has a pair of IFs going into it. And that's how it essentially puts everything together. The rest are a bunch of DC-DC converters. These linear micro module switches are great, and they're quite expensive actually. and a whole bunch of DC-DC converters up here. These are all separated from the RF board. There are no components on the other side of these boards, by the way, and that gives them some nice isolation as well, because it completely essentially they have two ground planes facing each other, which is good, separating all the digital activity. Here's our RU10 Intel or Altera FPGA. These are a few $1,000s, even in a reasonably large volume, so they're quite expensive. And we have a GPS module, as this thing, of course, has GPS. And there's a bunch of other mixers and switches and filters in here to clean up the DDS signal. If I were to just go through the details of how this is completely built, it will be an hour and a half video just going over every single decision that has been made here. I'm just impressed that this thing can be put together as well as it does and work as well as it does. So now that we have a good idea of how this works, we should be able to test it. Now there's one subtle point here that I want to add. In the instrument, where you do have the IF option, you actually do lose the upper end of the mixer range. So if you don't get the IF option, you get the sweep all the way to 43.5 gigahertz. But if you do get the IF option, you get a 1.5 gigahertz IF output, but then you lose the upper few gigahertz range, and that's because you lose the IF digitization of this final mixer. That's a bit of an unfortunate. That's probably my only real criticism of this architecture, and that's because they just couldn't fit another switch here to be able to allow that to happen, to be switched as well. But then you get the 800 megahertz analysis bandwidth, which we will do a complete experiment on, because it's a unique feature and very useful for the upper millimeter wave range frequencies that this thing supports. So I think we have a reasonably good idea of how this is put together now. Let's go and play with the instrument. Okay, so for our first experiment, let's try and characterize a pulsed radar module. This is a 24 gigahertz pulsed radar module from Infineon. I actually did a complete analysis of how this IC works. We even took it and looked at it under the microscope, but we never looked at the signals that are coming from it. Now we're going to use the Signal-Hound to actually analyze it. Now in front of it, we have a fairly large horn antenna. This is actually a 26.5 to 40 gigahertz antenna. This is a 24 gigahertz radar, but it will be okay for our purposes. It just won't have a perfect gain calibrated there. And we have the signal just simply directly connected to the input of our spectrum analyzer. We have the Ethernet cable connected, and that's about it. So we can actually now go ahead and analyze the signal coming from this, but we can get some surprisingly good information about how this chip behaves dynamically, and we can all do it from the Signal-Hound software. So here's the GUI that controls the radar, and right now the radar is sending out very, very narrow pulses, only 4 microseconds wide. So that makes it already a little bit difficult to capture, but the radar gives you a whole bunch of information. Now this is not the focus here, but there is an interesting phenomenon that's worth noting here in the radar. So if you look at the FFT magnitude, which is the radar's computed return signal there, you can see that it has this periodic behavior. Now remember that the radar is looking into the horn, and the horn is connected to the input of the spectrum analyzer. The spectrum analyzer is constantly sweeping, and it has all these front-end switches that are constantly changing. Now from the radar's point of view, the VSWR of the antenna is constantly changing too, and there may even be a little bit of leakage signal coming back out. So that looks like this periodic signal. We can verify that that's indeed what's happening, because if I go over here and just do a single measurement, so there's no dynamic behavior from the GUI of the spectrum analyzer, you can see that that actually stops, which is pretty interesting. So the radar is actually measuring some changes of effect of the input. Now this is really weak, remember. This radar, of course, has high sensitivity. So let's go back over here. Let's put this into auto. So right now we're looking at the regular spectrum analyzer. Now notice, as I said, that this thing now stops at 40.8 gigahertz, not 43.5, as we discussed why that is, and that's because this one has the IF option. So we have the complete sweep here, and every once in a while you see a small activity, and that activity is the radar. And these are 4 microsecond pulses. It's not surprising that we're not catching them all the time, but every once in a while there will be something. But let's go ahead and change this and put it into real-time mode. Now in real-time mode, we have a much better chance of catching these pulses. There you go, there was just one that we just saw. And here we have a 100% probability of intercept of pulses that are 35 millisecond. This is orders of magnitude longer than the pulses we were still looking at. And you can see that the pulses are actually strong enough that we get that IF overload here. So we should just increase that reference a little bit. Oops, the other way. You go -10 so that we don't get that IF overload. But every once in a while you can see that in the spectrogram we see a tiny, there you go, there it is again, a tiny behavior. So let's go ahead and put a peak marker here. Let's enable the peak tracking marker so that the first time we catch one, there it is, that was the marker. You can see the marker will now jump over there every time we catch it. But the frequency of it is around 24 gigahertz. So let me remove the peak tracking here, go over this and say 24.125 gigahertz. That's the center frequency of the radar. we're going to reduce the span considerably to about, let's say, 160 megahertz or 100 megahertz, and these are our pulses. There it is. Now we're looking at the average acquisition detection here, and that's why you see the behavior. Now right away from the spectrogram, you can clearly see that these are pulses because there's narrow gaps between each of these individual pulses. Now in this mode, while we can get a lot of information, it doesn't help us understand the exact behavior of that pulse. And by the way, I want to note that the software is actually not a very heavy in terms of installation, so there's so much feature and it's ridiculously fast, which is fantastic. That's what I always like to see. There's just a lot of bloat in it. It works really, really well. So let's now change the analysis mode once again and actually now do a zero span. In zero span, we fix the LO sweep and we look at a single frequency. We can do all kind of analysis on it. One minor thing I forgot to mention, if you go to full span, let's appreciate the fact that we are sweeping from nearly DC to 40.8 gigahertz in 34 milliseconds. That's absolutely crazy, and which is one of the strengths of this instrument, of course. Let's go ahead and center this a little bit better. I'm going to enable the peak tracking. I'm going to go back into center and turn it off. And now we're going to go into the different analysis mode of the zero span. Now in zero span right off the bat, we're going to get a whole bunch of information, different kinds of analysis of the signal as a function of time. At the top left, we have the amplitude versus time, which is very helpful. We can see the individual pulses that we were talking about. And even though we're capturing about 1 millisecond, you can see the 1 millisecond sweep time here, and inside this menu, we see multiple pulses, which means these pulses, even though they're very narrow, they do repeat multiple times within 1 millisecond, which makes sense for a radar. Now the entire time overview is also at the bottom right over here, which is the entire capture time, which is also 1 millisecond at the moment. Waterfall is there, of course, frequency versus time, and the spectrum. The spectrum comes and goes, depends on the duration which you're looking at, whether there are any pulses actually captured in that duration. Now this is moving around too much. It's going to be difficult to see. The very first thing to do is to trigger on this, so we have something reasonable steady on the screen. We do have multiple triggering available, of course. We can do a video trigger, and you can see the pulses are around, let's say, minus 30 dBm should be good enough. We can trigger at a level of minus 30 dBm. There we go. At a trigger of 10%, you can see the very first pulse placed right over here. Okay, that looks all great. Let's go ahead and zoom in a little bit more on this. Now we are looking at the FFT settings and the actual measurement time. 1 millisecond is a long time. Let's set that to 100 microsecond, so we can actually zoom into one of these pulses. We can put that over here, and we can actually move that right back. So you see how easy it is to capture an individual pulse that you have triggered on it. And there's our pulse. Look how nice it is. We can see the exact dynamic behavior of our pulse coming from the radar and how quickly we can get to it. There's a couple of interesting things to note right off the bat. The first thing to note is that if I look at the waterfall, we can see multiple unique features right away. We see an area where the signal begins to be present, then there is a little bit of quiet time, and then there's big frequency spread here, and we can find out how much that is, and then there is another period right after it. Now I can move a marker on this very easily, and from this point, we're at 24.083 gigahertz. You can see that at the top right, and move it all the way on the other side, 24.208. So it's not a very big frequency span, but it is some pulse spreading. And that's important for a radar because you want to make sure you're still within the window. So we want to analyze that a little bit further. Now, if you go into the amplitude versus time, we can see some interesting features of this right away. So let's place a marker on here at the very beginning of the pulse. We can also create a delta marker and move that delta marker and put the main marker here. You can see the pulse is about 3.6 microsecond, which is a little bit less than what the radar actually telling us. But more importantly, it does have some interesting characteristics. So let's move it over here and let's zoom a bit more so we can see exactly what the pulse is doing. So let's think about what a radar like this wants to do. This wants to be as low power as possible. So it doesn't want to do anything when there are no pulses. And I think what happens internally is that it turns the VCO on, the VCO stabilizes, and then it turns on the power amplifiers to its maximum gain, transmits the pulse, turns the PAs off, and then goes ahead and turns the VCO off. It does it in multiple stages, and you can clearly see that characteristic here in the pulse shape. You can see we are putting out a little bit of power, and then the power jumps out significantly. Remember, the delta between these two is huge. We're talking about tens of dBs here. And then it's flat across the entire pulse, which is good. Then it drops, and there's a little bit, and it drops again. Now, during this time is most likely just leakage from the chip itself, because even if you turn the power amplifier off, I think it's only 1 or 2 stages, you still get some leakage out, and that leakage isn't necessarily very well controlled. That's exactly what happens during this. So by looking at this pulse so quickly with the software, you can measure exactly the individual characteristics of how those pulses behave. And you can also see that there is a little bit of changes in spikes in the amplitude variations as things come and go, because when you turn these on, of course, there's brief moments where you have some dynamic behavior from PAs powering on. They're not exactly fully correctly biased yet, and you get some of these interesting behavior. But I'm also very much interested in seeing what happens to the frequency, because that is a pretty important characteristic of a radar, and you don't want it to go outside of the ISM band where it is allowed to transmit. So let's go ahead and zoom in here. So this is a very large frequency range we're looking at. We can do the same thing and zoom into this one as well. I think the rotation of the wheel seems to be anti-intuitive. It's backwards to where I would expect it to be. Yeah, I always turn it backwards first. And if I look in the middle, you can see what happens during the transmission of that pulse. Now, during that transmission, the frequency does change a little bit. That's changing by about a couple of 100 kilohertz. Now, for a short-range radar like this one, this probably doesn't matter anyway, because it's not going to affect the FFT being taken. It's not going to affect with the Doppler radar because the range is so small. But nonetheless, you can see that indeed there is a little bit of frequency variation while this pulse is happening. Now, I can do all of this very, very quickly with the software, with just moving around a few windows and enabling and disabling various measurements. And that's testament, I think, to how well this is thought out. A couple of minor things that would be nice to add here is, for example, showing what each of these divisions are in time, because it just gives you a start and stop. It's hard to know what the delta t is in one of these. It would be nice to show that. I don't think I see it anywhere in this. And it would be also nice to have perhaps a way to show, if you're looking at this window versus that window, where that is in the time versus view, because I can move this left and right, and I'm not sure where I am looking, and if these are not correlated with each other. It would be nice if there was a way to lock these two together. I don't think I found a way to do that. So then, for example, when you scroll this would scroll with it if you want to. So, you're looking at exactly the same places. Right now, I believe that's what's happening, although there is a line here for the trigger, so you could find a line in this one as well. And then you should see individual ones, although I don't see the line in this one. So I have minor couple of tweaks there can be done. Now we can also capture a much longer period if you want to. Let's say we capture a 10 millisecond period, which is a much longer period, and then we now can also move this, for example, around. If I can catch the right one, that's what happens when it's exactly at the corner. So let's put this at 50% trigger. There you go, there's our trigger line. And let me see if I can move this. Yeah, it's hard to move it like that. We might have to increase the length. When the two windows are locked up to the corner, it makes it difficult to capture the one that you want. So let's make this 1 millisecond, so it's a bit larger, and then we can bring it where we want. For example, capture multiple of these at the same time, like that. And then you can see now the individual ones that are much easier. And if I go out to zoom on this one, we should be able to capture some of these pulses. There you go. These are the pulses in the time domain. So that's why I was talking about a little bit of correlation between these windows would help. But very nice and easy, very fast. The software works really well. We can also quickly verify that the pulse is indeed adjustable from the radar GUI. We go over here. Let's turn the pulse from 4 microseconds to 10 microseconds. Press apply here. If you go back, you can see that the pulse is indeed quite a bit longer. So this is exactly what we would expect to see from this. We can move that a little bit to center it around the pulse, and we can see the complete pulse. We can look at the slightly longer window. It looks good. So the radar is doing exactly what we were expecting. Now the arming and the disarming part of the radar doesn't change no matter how long the pulse is, because that's independent. That has to do with turning on and off the internal blocks, which is again consistent with what we would expect from the chip. Measuring the channel power is also pretty easy, because we can enable the channel power measurement individually over here. We can make that a little bit larger as well. And right now we're sending the 4 microsecond pulses. Now the average channel power is minus 25 dBm. Now I would expect that number to go up if I make the pulses longer. So I can go ahead and make the pulses back to 10 microsecond and apply that and go back, and you can see now the power is minus 21.9 dBm, because they were turning on more power per pulse in this case, because the pulse is longer, and this of course has no issue capturing that. So let's go ahead and use the noise figure personality of the Signal-Hound Spectrum Analyzer and measure the noise figure of this broadband Unritsu amplifier. This is a 30 kHz to 10 GHz amplifier. It has about 25 to 28 dB of gain. I want to measure its noise figure. Now, the instrument is capable of performing Y factor noise figure measurement, but it does not have a 28 volt output. It doesn't have the smart noise sensor interfaces, which means that you have to power the noise source from an external power supply. But the instrument's personality walks you through all the steps, and I'll show you that in a second, in order to be able to do that. So in this particular setup, I have the noise source directly at the input of the amplifier. The output of the amplifier goes into the input of the spectrum analyzer, and then we have a couple of power supplies over there. The top one's going to act as the 28-volt power supply for the noise source, and the bottom one is going to give us the plus and minus power supply required to power the under 2 amplifier. So let's take a look. So the noise figure personality can just be simply accessed from this drop-down menu. And I want to emphasize that all of these capabilities that you see here are standard with the Spike software. You don't have to pay for them separately, and I hope that never changes. But once you install the Spike, all of these things are there by default, which is fantastic because, as you know, these things are often quite expensive from competition where you have to buy them each individually. So here's the noise figure personality. Now I've already done the calibration to save us some time. You can see the cal state is valid. That's why it's a green cal written there. But it's really quite straightforward. So what you do is that you basically create a ENR table for your particular noise source. This noise source that I have is an HP346C. It's a fairly old one, but it works up to 26.5 gigahertz. I've already entered the ENR tables, and you can save that. And recall, you can have many of them at the same time. And this instrument also allows you to have a different cal noise source than a measurement noise source, which means that it is fairly friendly for measuring things like mixers and nonlinear conversion, but I could not find that anywhere in the menus where you specifically say I'm measuring a mixer, and I hope they add that because it's a pretty low-hanging fruit. In order to add that capability, they could use, for example, this space over here to show the setup so you know which one you're measuring, and you can have an external LO to do down conversion so that the instrument knows exactly what's going on, and you can do, conversion noise figure, which would be great. But right now we're just measuring an amplifier. Now, one other thing I want to highlight is that I just measured something which is incorrect, and you can see it says invalid over here. So it checks to make sure that between the noise source status being on and off, that you do actually see a sufficient difference, and that ENR table does really reflect a difference in the output power spectral density so that your noise figure is accurate. So I like that it tells you this so you can't make a mistake. Right now we have set our reference level to minus 50 dBm, so nice and high sensitivity at the input of the spectrum analyzer, because this is a fairly low noise, relatively low noise amplifier, and we're measuring essentially the entire range from 100 megahertz to 26.4 gigahertz. So I've already done everything, so let me go ahead and turn the amplifier off, and on I should say, and then we can go through the procedure. So the amplifier here is turned on, so we're going to say measure, and let's see what it says. So it says connect the DUT to the spectrum analyzer. We've already done that. Press OK. It says turn the noise source off. The noise source is indeed off. We're going to go OK. It's going to make one measurement, the cold measurement, with the noise source turned off. Now it says turn the noise source on. That's pretty easy. Here's our noise source has been turned off, applying 28 volts to it, and we measure it again one more time. And there it is. Here's our noise figure. Pretty nice. Let's take a look and see if this measurement actually makes any sense. So as you can see, within the bandwidth of the amplifier, the noise figure is pretty good. It's about 4 dB or so. And then once we're around over here, which is around 10 gigahertz or so, the gain of the amplifier begins to drop. And once the gain of the amplifier drops, of course, the noise then starts to climb pretty rapidly. Now, this amplifier is really only rated up to 10 gigahertz, which is up to here, and you can see has a nice flat gain response just under 25 dB or so. There's a little bit of loss in that cable, which is not included. That's a different story on calibrating. But then once you have that, the noise figure is pretty flat. That does go up a little bit at lower frequencies as well. And then that's it. You have a very nice, simple noise figure measurement, and you get the gain and the noise figure at the same time if your calibration is valid. And these little quiet checks that are built into it, I really like that. Make sure you don't make any mistakes. You also get your table over here, all the frequencies that you see, and you can change various things like averaging and so on. You can also make a spot measurement if you're interested in measuring the frequency or the noise at only one point. So very nice, simple. I just hope that they add that mixer as well and a few little GUI interfaces in there to know exactly what you're measuring. That will be a pretty powerful noise figure personality. Well, we may as well use the phase noise personality as well and measure the phase noise of the instrument itself. I'm going to use the Signal-Hound PNCS1. I've done a full teardown and review of this unit as well. This is a 1 gigahertz phase noise standard, so it has an exceptionally low phase noise. Whenever you connect it to pretty much most spectrum analyzers, you will be able to measure the spectrum analyzer's internal phase noise because this one is so much better. So we have it directly connected to the input. This is at 1 gigahertz, and now we get to go and use the personality and find out if this thing meets its specification. So here's that 1 gigahertz tone in regular sweep mode. You can do a peek on this to see where it is, and it is indeed very, very close to 1 gigahertz, and that's because the internal 100 megahertz OCXO of the spectrum analyzer that I showed you is also very accurate. So these things are in pretty close agreement with each other. Now we can also go over here and go to phase noise. There it is. Here's phase noise, and it's been running in the background because I already tried it out. And there you go. We're measuring it at 1 gigahertz. I'm measuring from 100 hertz to 10 megahertz, and it has all the basic phase noise measurement capabilities you would expect. There's two traces here, one that's averaged and one that is the raw measurement. Now it does have quite a bit of variation on the raw measurement, but once you average it out, it kind of hugs the middle value of it, which is roughly normal. I would have liked to see a little bit less variation at the lower frequencies there. But if you look at these numbers, they're actually better than the specification. Now that might be because the unit is running reasonably cold. It's running at 35 degrees Celsius right now. And I think that the specification just makes sure that it is better than that throughout the entire temperature range. But we're looking at a phase noise of, at 1 megahertz, about minus 141.5 dBc per hertz, which is quite good. And at 1 kilohertz, minus 132 dBc per hertz. And the PNCS1 is better than that. So we're basically definitely measuring the spectrum analyzer itself. You can also measure calculate the jitter from that, and you can see that the jitter calculated from 1 kilohertz to 1 megahertz is 22 femtosecond, which is very, very small, as to be expected from a really good spectrum analyzer and a really good phase noise standard. This is what you would get. So it's a nice little addition to the software as well. So let's go ahead and do some more complex analysis. We're going to take a look at a millimeter wave mixer and see if we can analyze the kind of signal it produces. Now there are a lot of instruments turned on here in the lab, so I hope the noise isn't too bad. Now for our IF input into our mixer, we're going to use the Rohde & Schwarz SMBV100B, which is an exceptionally clean vector modulator synthesizer box, and we're going to generate a 64 QAM modulation on a 3 gigahertz carrier. This thing can produce really low EVMs. I use it in the lab all the time. And that's going to be the IF input going into this millimeter wave mixer. That mixer is going to be clocked using an LO at 25 gigahertz coming up there from the Rohde & Schwarz SMP04, and that's going to produce an upper and a lower sideband signal at 28 gigahertz, and 28 gigahertz is of course one of the 5G new radio bands, so we're going to be able to use that. And here of course we have our SM435C from Signal-Hound, and I also put a little fan on top of it. This thing does get pretty warm, about 50-55 degrees Celsius, so this is going to help run it a little bit cooler. So in this setup we have our modulation coming in at 100 megasymbols per second. So it's going to occupy just over 100 megahertz of bandwidth. In that situation, we are within the bandwidth of our analyzer, so we should be able to use the built-in functions to look at the modulation and constellation performance. And here's the output spectrum from the mixer. Now, as to be expected, we have our LO feed-through, which is very large. This is not the greatest mixer in the world, but we also have the lower sideband and the upper sideband signal. The upper sideband signal here at 28 gigahertz is what I'm interested in to look at. Now, this is a regular sweep from the instrument. We can put it into real time, of course, and then we can reduce the bandwidth, and we can take a look at the signal a little bit closer. And there it is. And here's our modulator signal. You can see there's a little bit of a ripple on it, and that ripple is a combination of the response of the vector modulator and of course the response of the mixer itself. So I want to take a look at this constellation and actually do a demodulation, find what the EVM is. Now this instrument has that capability built in. We can go into the digital modulation analyzer and take a look at it. It's already been set up in order to save some time. And you can see that our symbol rate is 100 megasymbols per second. And I'm looking at 4096 symbols, which is a sufficiently long duration of symbols to give us a good statistical result. Everything else is pretty straightforward and explanatory. Now, this digital demodulation capability is good using the Spike software. It's not as good as something like the Keysight VSA, but keep in mind that this is free and it comes with the instrument. You can always capture this data and analyze it, of course, yourself. The equalization is enabled with 31 symbols, and you can see that we're getting a fairly nice EVM, about 37 dB SNR on this. So under this situation, because the bandwidth of the signal is within the maximum bandwidth of this instrument, which is 165 megahertz, we can do this demodulation without issues. We can look at the EVM versus time. We have the equalization response, and you can see we do indeed have reasonably aggressive equalization that's required because the mixer is not flat at all. We get the INQ channel I diagrams, and it runs pretty nicely on this computer, as well as of course the software itself. But what if I increase the bandwidth beyond 165 megahertz? And that's exactly where the external IF comes into play. So let's change the setup, increase the modulation bandwidth, and see how we can use other instruments to analyze this beyond the 165 megahertz bandwidth. So let's now continue our analysis, but now we're going to use the Keysight M8190A to generate our IF source. This instrument does have digital up conversion capability, so we can actually create an IF carrier up to a few gigahertz, and then we can put any modulation we want on top of that with a wider bandwidth. So I'm using 3 gigahertz again, 64 QAM, but this time at 250 megasymbol per second. And that goes in exactly the same way to the mixer as before, and of course that's connected to our spectrum analyzer. But instead of using this internal analysis, because it doesn't have enough bandwidth, we're going to use the wideband IF output option of it, and that goes to all the way over there to channel 1 of the Keysight MXR, which itself has digital down conversion. I've done a full review and teardown of that instrument. It's an 8-channel 10-bit converter built in. It's a fantastic instrument with a lot of capabilities. It also has real-time spectrum analyzer that you could use in exactly the same mode. So let's take a look at the VSA and see how that looks when we have it configured like this. And in the Spike software, we can see that indeed we're occupying a wider bandwidth. We're looking at a 500 megahertz span here, but in this span is now going to be too wide to do direct demodulation. So what I can do is I can go to utilities and I can enable the IF output. And now the instrument acts as a low noise, low phase noise down converter. And it's going to put that on IF at 1.5 gigahertz. And you can see I can define the carrier here, which is defined as 28 gigahertz in this situation. And that should produce our IF now coming out, and it should be visible on the oscilloscope. So if I switch to VSA, which is already configured, you can see if I go to the frequency setup of the VSA, we're looking at 1.5 gigahertz. And we're looking at a 400 megahertz bandwidth, which is wider than what the instrument originally could do. And there it is, look at that, that's our constellation. 250 megasymbol per second, 64 QAM. We're getting a pretty good EVM, about 33-34 dB of SNR. And you can see the equalization is correcting for the cables and the mixers imperfections and so on. So using the wideband IF, I can use any digitizer outside of the SM435 to digitize now my up to 800 megahertz of bandwidth anywhere in the band. So that's quite powerful now, which means that we're not directly limited by its internal bandwidth anymore. We can use other available instruments in the lab. So the Keysight MXR has a lot of capabilities. It also has a real-time spectrum analyzer, as I mentioned, but there are other very powerful oscilloscopes that can be used to enhance the capability of the SM435. Now let's take a look at the Tektronix one, which also has some nice tricks up its sleeve. So now let's take advantage of the Tektronix 6 series to do a similar type of digital down conversion analysis. The Tektronix 6 series has a lot of functions that take advantage of the DDC, and it can do some pretty neat analysis directly in the instrument. So I'm basically connecting now the wideband IF signal to channel 1 of the Tektronix, and we're going to experiment with a different kind of waveform. What I've loaded from the M8190 is now a very rapidly frequency hopping signal. It hops over 300 megahertz very, very quickly, still centered at 28 gigahertz. And this is now beyond the analysis bandwidth of the SM435C, which means that we can use the IF output and go over here to analyze it. So first, let's take a look and see what does the instrument directly report and what else the Tektronix 6 series can add to the analysis. And here we are again, and you can see that in the real-time analysis, these tones are all present. But they're not actually present at the same time. They're hopping very rapidly and they live for a very short time, making them quite difficult to detect. And the fact that this peak is jumping around is some indication of that. And you can clearly see that there's some very complex dynamic behavior is happening among these different tones. Now, if under analysis mode, if I go to zero span, which I've already set up, this zero span is going to now limit us to 165 megahertz, which is exactly the analysis bandwidth. Now, once again, if I look at the FM versus time, there is clearly a step that's happening between those tones. You can see they're jumping up, and then there is a period in which nothing seems to be happening. And that's because those tones are now outside of the analysis bandwidth of our instrument. As a result, we're missing them and we don't get to see the complete ramp here. But if we had more bandwidth to analyze, which of course the Tektronix MSO can do, we should be able to use its internal functions, which are very similar to this, to be able to do a complete analysis of that and be able to see this. Now I can move this and we can take a look at one window, for example. From here to here, you can see very clearly that this is visible. And if you look at the waterfall towards the edges, it begins to become dim. And that's because there's an attenuation associated with the outside filtering of the span. So you don't see as much of a tone. There's an artificial attenuation there. So let's go back over here and enable our IF output once again. And this time we're going to switch the window of our Tektronix. And check it out, I've already set it up and we're seeing a very similar analysis being done directly inside of the Tektronix. Now, in my view, Tektronix's digital down conversion as a software inside the MSO6, for example, there's really nothing else like it in the industry. And it makes it a perfect companion, for example, to something like the SM435C because of its similarities and the incredible analysis it can do. Now here we're looking now at a much wider bandwidth. We're looking at a 500 megahertz analysis bandwidth. This can go up to 2 gigahertz, so this is not a problem at all for it. And we see the complete ramp now. And you can see that the steps go all the way up and then jump back down, all the way up, and there is a plus and minus 300 megahertz of sweep there, which is far above the 165 that SM435C could show us. So this shows again that an external digitizer with its own sophisticated DSP can accompany this instrument and do a whole bunch more. And this is just the tip of the iceberg. There's so much more you can do in this instrument. You can also plot phase versus time. And in some ways, it actually has features that the SM435C Spike software doesn't quite have. It can trigger on the frequency versus time. It can trigger on the phase. It's really quite sophisticated. If you haven't seen the review of this, I definitely recommend that you watch that too. There's a lot of cool stuff in there. There are also a lot more features built into this Spike software. For example, we have an EMC pre-compliance function. We have interference hunting, which is quite good on this instrument because it has such a fast sweep rate, make it very easy to catch anomalous readings. You can record it and then figure out what is outside of the usual trend that you're seeing. It has features that allows you using the GPS to build a map and then go around and make different measurements, and it will populate a map for you, showing you what kind of emissions and what kind of spectral content you observed in the field, which is very useful, and that's why it does have a GPS. And there is a mask emissions you can of course define, and it does have a few demodulation of particular standards in there, and they continue to add the new features to it. It will just take forever to go over everything else. And there's recording functions and playback functions, which I showed in the previous video, so I'm not going to go over it again. But in terms of feature set and functionality, in my view, this is basically a dream software-defined radio, especially if you take advantage of the API, grab the data and process it yourself. There's some pretty crazy things you can do with such an instrument with such a fast sweep and so much bandwidth. And there you have it. I hope you enjoyed this extensive review of the latest Signal-Hound instrument. These things, like I said, are a dream software-defined radio, and allowing you to even deploy it remotely with fiber and monitor spectrum anywhere with the API. They really push to the edge of what is allowed with ITAR. Above that, you get these fast-sweeping spectrum analyzers that cannot be sold without ITAR classification to a lot of users. So it's a really fantastic instrument from that side. And I love the fact that they're putting so much pressure on other vendors, bringing themselves into the millimeter wave era. And I like to see what they do next. There's a lot of interesting things that these instruments can expand into. As always, let me know what you think in the comment section, and thanks again to the Patreon supporters, which make a lot of these experiments actually possible, and I'll see you next time.